And so the waveguide dispersion tends to shift the zero dispersion point a little bit further up from 1300 nanometers when we have a real optical fiber. Okay, a couple of equations that we can write down to further this picture and to give you the total picture is that delta tau by L modal for step index fibers, well, we've already seen this equation, is N1 delta over C, and that delta tau by L for GRIN modal for GRIN fibers is N1 delta squared over 2C. Okay, so these two equations are important. This first one we had back in Chapter 4. It was just given to us. And here in Chapter 5, they just give us the equation for the GRIN. But what's important is to note that the GRIN delta tau by L is much less than SI delta tau by L, due to the fact that it's essentially the same equation, except it's another factor of delta over 2, since deltas are small. So the delta for most waveguides is on the order of a few percent at most, typically less than 1% even for the fibers we look at. So this is why, so this equation tells us why essentially all multimode fibers have a GRIN index profile, because it lowers the pulse spreading per unit length by a factor of maybe 50 or something like that. Okay. And so finally we have a fairly complete picture of pulse spreading in optical fibers. What I'm going to do now is I'm going to show you that we can put all of this together into a spreadsheet. And this is in the handout from Chapter 5. And I hope you can read this here. I hope it's not too small. But basically I've made a spreadsheet, and I'll sort of talk you through the calculations that go into this spreadsheet. And I will recommend that you make a spreadsheet like this and you use it for the problems in Chapter 5, as I mentioned in the homework sheet itself. So I'm recommending that you use the spreadsheet for these. So let me talk you through the spreadsheet. Basically what we're given is we're given the two refractive indices, N1 and N2. We're given the wavelength and the spectral width of the source. So this is lambda. This is delta lambda. Okay. We're given, and we go ahead and we calculate the delta. Okay. So this is the waveguide delta, and it's calculated from N1 and N2 using the equation that we had. Okay. We're also going to use as an input the zero dispersion wavelength as 1300 nanometers in most of these, in all cases here, but that's also an input. And what we're going to do is we're going to use the Meyer equation to calculate the material dispersion. And so this material dispersion is from, this row is from the Meyer equation. Okay, and it uses that zero dispersion wavelength as part of its calculation. I guess we could give the zero dispersion slope as another input, but I think I've set that to a constant in this spreadsheet. And now we also have the waveguide dispersion, and here I'm just leaving this as an input that you can type in, and I say read from figure 5.25, and that's the one I showed on page 150. So I've basically just used that as an input. Okay, type in those values. And And so finally here I calculate the total dispersion, which is simply the sum of the material and the waveguide dispersions. And then finally, from the total dispersion, I multiply by the spectral width to get the dispersive delta tau by L. So this is delta tau by L dispersive. Okay? And this is in picoseconds per kilometer. Then I have a variable which tells me what type of fiber I have. Do I have single mode? A 0 is a single mode. A 1 is step index multi-mode, which we don't use so much. Number 2 is a grin multi-mode. Okay? And basically what I've got is I've got an if statement in my spreadsheet which uses one equation or the other. If it's a single mode fiber, I'm going to go ahead and use this equation for the modal dispersion. No, if it's single mode, if it's multi-mode step index, I'm going to use this one. If it's multi-mode grin, I'm going to use this one, this equation. If it's single mode, hey, I've got 0 modal dispersion because there's only one. And so I just have an if statement which gives me either 0 or applies one of those two equations to get the modal delta tau by L. The modal delta tau by L calculations is very tricky because when you use these equations and plug in the units, you're going to get seconds per meter. And you've got to switch the units over to picoseconds per kilometer. And it can be tricky, but it is straightforward, and my spreadsheet does that for us. Finally, it calculates the total delta tau by L by adding together the dispersive and the modal components in the Pythagorean squared sense. And so here's my total delta tau by L. And you can see here the advantage of the grin multi-mode over the step index multi-mode. Step index multi-mode has this huge modal pulse spread per unit length, whereas grin multi-mode has a much more reasonable pulse spread per unit length. Of course, single mode fiber wins hands down in its pulse spread per unit length because of the absence of any modal dispersion. Finally, I'm simply using the equations for the bandwidth distance products, and again, the units are tricky on these things. If you use picoseconds per kilometer, you're going to get terahertz per kilometer as the units, because pico is 10 to the minus 9th, terahertz is 10 to the plus 12th. No, picoseconds is 10 to the minus 12th, terahertz is 10 to the plus 12th. So if I just plug in the delta tau over L in this equation with units picoseconds per kilometer, the out comes kilometers per picosecond or terahertz kilometers. If I divide that by 1,000, I get gigahertz kilometers. And that's often useful to put